All right, thanks very much. Thanks for coming also today. And today we essentially, yesterday we considered a class of simple systems, so classical magnetic systems. And what we essentially used is an idea that is quite common in physics to derive differential equations to describe some physical quantities. So we show that if you take like the Potts model, although it's in mean field, okay, mean field, and it is actually a slight variation of the standard Potts model. So if you look at the partition function, which I call Zn, where n is the size of the system, we proved that the partition function satisfies a PDE, a linear PDE. Is a solution of a linear PDE. Okay. In particular, in the simplest case, it was the heat equation. Okay, we could integrate it and calculate all the observables. In the thermodynamic limit, which means n, if you send n to infinity, the partition function is not the right function to consider. You need to introduce a properly rescaled variable, which is the free energy, 1 over n log of Zn. And then you discover that some observables can be, the main observables of the theory can be calculated as derivatives of the partition function. In particular, we had the derivative of Fn with respect to a variable that was interpreted as the coupling with the external field gives you the magnetization, and the magnetization satisfies a nonlinear hyperbolic equation. In this case, in the simplest possible case, corresponding to the heat equation, this nonlinear hyperbolic equation was the Riemann-Hopf equation. So you have two coupling constants, which I call T and X, and then the magnetization satisfies this equation here. So with a particular initial condition that is specified by the model, so the magnetization at the initial time, so M is if you expand Nm in powers of 1 over n, okay, so M is the leading order in the contribution in the thermodynamic limit. In the simplest case, you have the Riemann-Hopf equation, and the solution is specified by this initial condition. So, and what we observe is that if you look at the initial condition and you describe M satisfies this hyperbolic equation, which evolves in the time where the time t is a nonlinear coupling constant, and then if you increase the time t, means to increase the strength of the nonlinear coupling. So the profile of the magnetization becomes steeper and steeper until you reach a point of gradient catastrophe. The gradient catastrophe corresponds exactly to the phase transition, the magnetic phase transition in this model. And then when you go beyond the critical point of gradient catastrophe, the solution becomes multivalued, and then you can recover the actual physical solution by a dissipative regularization, which corresponds to the diffusion in the heat equation. And then the dissipative regularization cures this singularity by introducing a shock transition, a steep shock transition, but still smooth in the middle of the region where the solution is multivalued. Okay, so the classical thermodynamics theory is nice because it allows to interpret the position, to identify without doing any calculation the position of the shock by placing it in such a way that if you look at the multivariate solution, it cuts two lobes of equal area. And this is the Maxwell, the famous Maxwell rule that he published at the end of the 19th century in Nature. Okay, so essentially what we want to do today in the context of the random matrix models and the connected so-called beta integrals and Lax equations, we want to see how this conceptual framework arises also in the context of the random matrix models, where we will see that things are much more complex, where the notion of integrability is not the classical notion of integrability in the sense of the linearization, because the Riemann-Hopf equation is linearizable by a nonlinear transformation, and so is the Burgers equation, its viscous regularizations. They are integrable by linearization. In the case of the random matrix models, integrability arises in the sense of Lax, okay, in the sense of the inverse scattering transform. And but you know, I'll provide details, details in this, a bit more details about this. So, what is the original kind of the story where this connection between random matrix models and integrability arises goes back to possibly 1991, due to the very to the famous work of Witten, who conjecture essentially of course Witten was interested in string theory, and he was in particular studying in detail a particular kind of topological quantum topological field theory, 2D quantum gravity. And where essentially the main physical object, the main object in the theory is the action S, which is expressed as an integral on the space on the space of matrix on the space of matrices of metrics on a particular manifold. Okay, so you have some. Okay, probably Witten use the. Yeah, I call it. I just use this notation. So you got some Hamiltonian there that depends on the matrix defined on this manifold. So I won't go into the details of this. I just want to convey the basic idea. So essentially, you have a problem of calculating some integral defined on a proper measure on a manifold, and the integral is calculated over all possible metrics defined on this manifold. And then Witten had actually more than one conjecture. So one conjecture was that two different formulations of 2D quantum gravity were equivalent. So one formulation was to define the 2D quantum gravity as the limit where you have a manifold, you take all possible, you take all possible triangulations, and then you take the limit where the size of this triangulation goes to 0, and then you expect to find some partition function. There was another approach based on translating this integral into this infinite dimensional integral into a finite dimensional integral on conformal structures. And these two different approaches, according to Witten, provided the same theory, okay, which according to Kontsevich who proved Witten's conjecture, was a bit strange. So I just wanted to quote what Kontsevich wrote because I found it funny. So the reason for this conjecture is an irrational, for mathematicians, in bracket, idea that gravity is unique. So there were these two approaches that provided some limit, and Witten conjectured that these two approaches would provide the same free energy. And according to Konciewicz, it's an irrational idea for mathematicians that, you know, gravity must be unique. Okay, I wanted to note it because I found it just funny. But the part of Witten's conjecture that is relevant to us is that when you define the action, okay, what the action is the partition function, and Witten conjectured that if you can identify the partition function with a particular function, very important in the theory of integrable system, and it is called the tau function for the KdV equation. Okay, I'm going to say more in detail what this means. So Witten conjectured essentially that if you take the partition function for this theory, in this theory you have a certain number of coupling constants, similarly to the case of the magnetic models. These coupling constants are standardly denoted as T1, T2, and so on. And Witten essentially suggested that if you calculate the function u, which is given by the second derivative with respect to the first coupling constant in this hierarchy of coupling constants of the logarithm of Zn. So this function u satisfies the KdV hierarchy. So with respect to these times. So T1 is interpreted as the space variable in the hierarchy. T2, T3, and so on are interpreted as the times of the hierarchy. The first member of the hierarchy is the KdV equation. So exactly written in this way. So ut2 times ut1 plus ut1 equal to 0. Okay, where the subscripts are the partial derivatives with respect to derivatives. So you see that we have ut2 plus ut1 plus a third order derivative. So it's different from the case we considered yesterday, where the higher order in the differentiation in the equation was of the second order. This means that the dispersion relation is complex valued, the equation is dissipative. In this case, the highest derivative is of the third order, the dispersion relation is real valued, and the equation is dispersive. Okay, so this equation is fundamentally different from the one we had in the case of the magnetic models. And then we have, on top of this equation, we have higher equations, which belong to the so-called KdV hierarchy, all compatible, commuting with each other. So it's an infinite hierarchy of equations. So as long as these coupling constants are, you consider infinitely many possible coupling constants in the model. And then the nonlinearities are progressively of higher order. Okay, so and in particular, this is very similar to, although in a different setting, to what we considered yesterday. The solution, this partition function, is identified with the tau function. So therefore, Zn is the tau function of the KdV, and but this is a particular solution of the KdV. So this particular solution is specified by a suitable initial condition. In the case of Witten, the initial condition, so where you set all the times, all the couplings to T2, T3, and so on equal to 0, is the identity, is equal to T1. So it's a particular solution to the KdV hierarchy, similarly to the case we considered in relation to the magnetic models. I have to note that if you do a proper rescaling and you put a small parameter in a way that you end up with a small parameter in front of the highest derivative, and you send the small parameter to 0, and this is actually the case when you do limit where the triangulation becomes continuous. So what we get at the leading order is exactly the Riemann-Hopf equation as in the case of the magnetic model. So the mechanism of a possible phase transition is very similar. The initial condition, of course, is different. So, as I mentioned, so Witten formulated the conjecture, and a year later, Kontsevich proved it in the case of the KDB. And then in the 90s, there was like a proliferation of results where people proved this correspondence between partition functions in statistical mechanical models, like random matrix models, and the tau functions of suitable integrable hierarchy of nonlinear partial differential equations, and or dynamical systems like the total lattice and generalizations of the total lattice. So that's a story that some of you know very well. Okay, so today we will concentrate on one particular aspect and see how things go more in detail. And since I want to go to look at the details, we need to consider a specific example, okay, where with a specific model. Okay, so first let's say, okay, what is a random matrix model? At least for what we need in this context. Okay, random. I will refer it to as a random matrix ensemble. Okay, what is a random matrix model? Is I define it as a pair of Mn is the space of n by n matrices, and omega is a function of a set of parameters, okay, which I use a vector notation for this set of infinite set of parameters. So omega will be a function of t1, t2, and so on. And omega is a measure. Okay, omega is a measure invariant with respect to a group of transformation. Okay, so omega is a measure invariant with respect to a group of transformation, and in particular, I will consider omega of the form such that d omega is minus some Hamiltonian. Okay, I call it Hamiltonian by analogy with the models, the statistical mechanical models we considered, and dm, okay, is the R measure invariant with respect to the selected group of transformation. Okay, so in particular, if this group, if Mn, so if Mn is the space of R Hermitian matrices, if Mn are the Hermitian matrices, so this means that so dm is invariant under the unitary group. Okay, so where U is an element of the unitary group. So consider a measure that is invariant under the group transformation. So actually, omega is invariant under the group transformation. So if once you have the measure, of course you can define a probability distribution. So omega, I'm looking for the omega of this particular form. So I'm integrating over the space of Hermitian matrices. So yes, I'm not sure.
Omega itself.
Omega itself.
You start with saying you have n.
I'm interested in the omega at this stage. Yes, yes. So, and I will focus on the main focus will be dm, which will turn out to be the Lebesgue measure on the space of matrices, and the particular form of this exponential. So that would be crucial in the example of I'm going to consider, which is the unitary ensemble. So in particular, so H, the Hamiltonian H, is of this form, okay, is the trace of m squared divided by 2 minus the sum where k is goes from 1 to infinity of tk m to the power k. All right. So this Hamiltonian is a formal expression because here we have this infinite sum, and of course the integral, in order to be meaningful, we need to have something that can be in principle converging. So in practice, what you do is to consider a model with a finite number of times, which could be whatever higher contribution you want to consider, of even order. We will see that it will have to be of even order to be able to define the integral. Right? So in practice, this means that take any theory with any number of coupling constants and fix it to be finite, whatever this is going to be. And in particular, so if t is equal to 0, okay, if we take all the t's equal to 0, so the ensemble, so this ensemble here is called, this example defines the unitary ensemble, so for short UE, okay? So this example defines the unitary ensemble with this Hamiltonian, and then if you take all the t's equal to 0, this corresponds to the so-called Gaussian unitary ensemble. Okay, so the measure, the probability measure, reduces to a Gaussian, and this is actually the first ensemble that has been studied in details in terms of the distribution of the eigenvalues of the matrices and so on. So, as I said, once you define the measure, you can define a probability measure, so a probability distribution, Pm of t, which is times dm, which is the exponential of minus hmt with this particular choice of h in dm, where Zn is indeed the partition function, so is the integral over the space of matrices, Hermitian matrices, exponential of minus h t dm. Okay, so this is the partition function. So so again, the partition function becomes the main object of interest because it's the function we need to know about in order to construct the probability distribution and do any subsequent calculations. So in particular, so we can define so in particular, the expectation values are calculated the expectation values are calculated in a standard way. So given given this notation, so it will be, so when I talk about the unitary ensemble, so the space Mn will be the space of the Hermitian matrices. So the expectation value, let me write it as the integral over the space of Hermitian matrices of Fm, which is where Fm is some function of your matrices, and times the probability distribution in Dm. Okay, so this is the standard definition of expectation value. And then we introduce the free energy, and would be Fn of t as given by 1 over n, the log Zn in dt. So the size of the matrices is small n this time, is the size of the system. I switched from capital N to small n because later I will use capital N as the typical scale for the large n limit. Okay, so I use, so small n is the n by small n by n is the order of the matrices. And once you define the partition function this way, I just as I said before, so minus the physical partition function would be minus Fn. So this in the physics literature you would have a minus in front in the definition of the partition function. But I will stick to this notation. So the expectation value, for example, if you define the partition, the free energy, the expectation value of the moments, the traces, the trace of m to the power k for some k, it will be equal to n times the derivative of Fn by tk. Okay, so this is quite obvious if you look at the definition of H. When you differentiate with respect to Tk, you construct the expectation value of the trace of the moment Mk. So this means that if you calculate the partition function of the free energy, you can work out these observables just by direct differentiation. So in general, for example, in the context of quantum topological field theory, the derivatives of with respect to the times are identified as the correlator of the so-called primary fields. So there is these are actual physical observables, okay, of interest in the theory. So a fundamental result, okay, is in random matrix theory is that I will keep the definition of the Hamiltonian here. So this is a classical fundamental result. So the partition function Zn function of t can be written as Cn divided by n factorial, the integral over Rn, the dn z to the power beta, the product where I runs from 1 to n. I will explain this in a moment. dzi. Okay. So the way it is defined, so the partition function is defined as the integral over the space of matrices. So it's an n by n dimensional integral. And this result tells us that actually the partition function can be calculated as just an n-dimensional integral over Zi, the Zi's, which are the eigenvalues of the Hermitian matrices. So zi's are the eigenvalues. So zi's are the eigenvalues, and Cn is actually, so I need to use, I put a beta here for a reason. So Cn is a constant that comes from the integration of the non-diagonal degrees of freedom of the matrices. Okay, so I will specify this in a moment. So Cn is given, can be written as 2 to the power n, okay, and pi to the power beta n plus 1 by n divided by 4 times n factorial, and then we have the product where k runs from 1 to n of the gamma function of beta k divided by 2 to the power minus 1. So the case if beta is equal to 2, so this is just a formula that gives us the explicit expression of this this constant factor that from the point of view of the theory is not really important, conceptually important. And then if beta is equal to 2, this is z, let me use a beta here. So Zn2 is the partition function for the unitary ensemble, okay, the example we will focus on today. But the same similar expression with a different value of beta returns to the partition function for different ensembles. For example, for beta equal to 1, you have the orthogonal ensemble. So, and if beta is equal to 4, for example, so this result, this partition function returns to the partition function when the integral is calculated over the symplectic ensemble. Okay, so the symplectic ensemble. So where the matrices are quaternionic. So, and these are essentially the three most important cases kind of studied in this context with real eigenvalues. So other choices of beta do not necessarily correspond to some nice ensemble of random matrices. Okay, this is what I wanted to say. So how do we prove this? Let me. At least I want to. I mean, this is a classical result. Probably it makes sense to sketch at least the proof, you know, to see why we can do this. And so essentially, so the idea is that we need to use the fact that the measure of integration is invariant under the unitary group. Okay, with the proof we do it for beta equal to 2, which is the unitary ensemble. So essentially we use the fact that dm, so we write m is equal to u times lambda u to the minus 1, where lambda is the matrix of the eigenvalues. Okay, so if m is an Hermitian matrix, we can write it as in terms of the matrix of eigenvalues by the application of a unitary transformation. And then dm can be written as, so then we calculate dm directly, okay, so we get du lambda u to the minus 1 plus u d lambda u to the minus 1 plus u lambda du to the minus 1. And then essentially we use the fact that du to the minus 1 is equal to 0, and then we can express this implies that du minus 1 is minus u to the minus 1 du u to the minus 1. Okay? So essentially, we use this property in, we substitute du to the minus 1 in the previous expression. So everything contains du. And then what we do, we choose u, okay, in particular, to be the identity. So we take an infinitesimal transformation around the identity. And this gives us, this means that every time you have u to the minus 1 or you replace with the identity, and we get that dm can be written as d lambda plus the commutator of du with lambda. Okay? So, and then now it is a point to look at the essentially to look at the components of this expression. So, because the measure dm is by definition the Lebesgue measure. So this is the product where I goes from 1 to m of the diagonal part times the product over iaj of the real part of dmij times the imaginary part of dmij, okay, where over I different from j. Okay, so essentially we need to calculate all the components of dm in terms of this right hand side. Okay, so what do we get then? So dm, so perhaps I can calculate, say, the component, so du lambda, okay, ij, okay, so we calculate, this is equal to the sum, just take the product, let's calculate the component ij of this product explicitly. So this is, this gives us dui ik lambda kj, okay, but lambda kj is the diagonal matrix of the eigenvalues. So this is the sum over k of du ik times z j delta kj. Okay, and then the only term that survives is du ij zj. Okay. Okay, we just calculated the product of matrices, and then you can calculate similarly lambda du ij. Okay, and what we get is zi times, with a similar calculation, du ij. So the commutator essentially depends on the difference between the eigenvalues zi minus j. So the commutator du lambda is just the difference. So zij minus zi times du ij. So the first part, this part is trivial, is I mean even simpler, being diagonal. So dm ij, okay, is dzi delta ij plus the commutator, which is dzj minus zi du ij. Okay, so this expression contains the Jacobian of a transformation from the Lebesgue, from the variables mij to the new variables, which are the diagonal variables, the eigenvalues, and the non-diagonal degrees of freedom, the uij. So the Jacobian matrix, what is it? We can just read it from here. It's a diagonal matrix which contains n ones, so 1, 1, 1, and then Uij contains 2n differences, Zi minus Zj. Okay, so we got entries Zj minus Zi, and then minus Zj minus Zi. So the Jacobian, the determinant of the Jacobian is nothing but the product where over I, for I and j running from 1 to n, okay, and strictly different from each other, of Zj minus Zi squared. Okay? But this is the van der Monde determinant of delta n z squared. So this is the van der Monde determinant squared. Okay? So let me just use a little space. So the van der Monde determinant would be the determinant, so 1, Z1, Z1 squared, and so on, 1, Z2, Z2 squared, and so on, up to Z, up to the power n minus 1. Okay. So this is the delta, what I denote here with the van der Monde determinant. Okay. So if we want to go from the variables m to lambda and u's, we have to calculate the transformation. We calculate the Jacobian explicitly. So the sorry. The partition function becomes Zn equal the integral over the emission matrices of minus h mt, and then we have the van der Monde determinant squared, okay, times the product of the diagonal variables, the eigenvalues, and then the product of d u I j, okay, for O I and j. Okay, so the key point here is that the Hamiltonian depends on the traces of m and its powers. So this means that the Hamiltonian does not depend on depends only on the eigenvalues. So the integration over u is just the integration of the unitary group. And this gives you the constant, so the constant of integration C, the constant Cn, and then this, you're left with just the n-dimensional integral on the eigenvalues. Okay, and then the formula follows. Okay? It's just the traces become just the traces of the sum of the eigenvalue. So the trace is just the sum of the over the eigenvalues. Okay, this gives us exactly the formula we needed. So the advantage of this is, of course, that we reduce the dimensionality of the integral from n by n to n, but also that the only variables we need to care about are the eigenvalues of the Hermitian ensemble. So if we had, for example, the symmetric ensemble, in the proof, the only thing that would change would be the fact that instead of du, we would have an orthogonal matrix, and instead of having n squared, the difference twice each time the difference of the eigenvalues, we would have this only once. So the result would be the modulus of the so delta n in modulus to the power 1. So it would be, we just have, the Jacobian just have it just has a smaller dimension. And this is why we get beta equal to 1. In the quaternionic case, we will have beta equal to 4 because there is more redundancy. So, all right. Now, I thought, yeah, it was useful to make sense of this in the first place. And then now I think what I can do is I can mention the first important result to establish the connection with the integrability. So, which is the determinant formula. So, in particular, the tau function. So, what I'm following essentially is the work of Adler and Moerbeke, who kind of worked a lot in clarifying and establish this the connections between unitary ensembles to the total lattice, orthogonal ensembles, the Pfaffian lattice, and the associated integrable hierarchies of PDEs. In particular, this would be the KP hierarchy and the Pfaffian KP hierarchy. So, let's consider now the partition function. I use the notation. I write the partition function as tau n, because this is the final end of this is to identify this function with the tau function of a suitable hierarchy. So I will use instead of z the tau function, but I will do this up to a constant. So I will call tau the partition function divided by this the constant from an integration over the non-diagonal degrees of freedom. So the object of interest will be therefore the integral over Rn, 1 over n factorial. Okay, this stays. Dn squared z times the product where I runs from 1 to n of rho zi t dzi. Okay, so where rho is a function of the variable z, and depending on the parameters t, given by the exponential of minus z squared divided by 2 plus the sum of tk z to the power k, where k is larger or equal than 1. Okay, so essentially I write here the Hamiltonian, the exponential of h, as the product in terms of the eigenvalues of these exponentials. So rho zt is calculated over the eigenvalues. Okay, it's just a different way to write the Hamiltonian once we consider the traces. So the reason why we want to do this at this stage is to make particular use of this one-dimensional measure of one-dimensional weight to define expectation values and or if you wish a scalar product induced by the probability distribution of the model. So let me explain better what this means. So what I can do, I can introduce, given this function rho, we can introduce the moments calculated. So Mn is a matrix okay, of size n, where the entries, I call them mu ij, where I and j run from 0 to n minus 1. And who are these mu ij? Mu ij are the expectation values with respect the expectation values of these variables, so z to the power I and z to the power j, where I and j run from 0 to n minus 1. Okay? So these are expectation values with respect to a particular measure associated to this function rho. Let me define this quantity so that it will be clear what we're talking about. This so Zi Zj is a scalar product. I use the subscript t to emphasize the dependence on the parameters. This is this integral over R, okay, of z to the power I plus j of rho in dz. Okay, so rho is a one-dimensional distribution, probability distribution induced by the Gibbs distribution on the space of Hermitian matrices, and this is just the moment of order I plus j. Okay. It's not normalized at this stage, so yeah. Up to it's a probability distribution up to normalization, and the matrix M is defined as the matrix of moments with respect to this scalar product. Okay, I shouldn't talk about probability distribution. Is the matrix of moments with respect to the scalar product, but of course we can write this, go further and write it in terms as a probability, work with a proper probability, a normalized probability distribution. Okay, so M is Mn is a symmetric Hankel matrix. Okay, so because the Mn of t, so essentially it's of this form, so is the expectation value the expectation value of z to the power 0, okay, with respect to t. Then we have the expectation value of z, so the expectation value of z squared, and so on. And then the second element here, just let me write, the next one would start from z to the power 1. So then we get z to the power 2. Okay, so the power is just the sum of row of the index positions on the row and the column, right? And you go on like this. So essentially it's an Hankel matrix because the second diagonals are all the same. Okay, and in particular, what I want to do, I want to keep track of each entry of the position of each entry, and I can do this by adding an index, a column index. Okay, so to these dummy variables. Okay, of course the integral will not care about what the z is called, right? But for the following calculations, I want to keep track of the entries by adding an index, a subscript to the dummy variables. Okay, but of course this and this are the same because because it's just an integral. So, and in order, let me. So Any questions? Is it all right so far? So essentially what we did here is we need to introduce this moments matrix, okay, defined in terms of this rho, which is a one-dimensional weight induced by the Gibbs distribution of the original model. And in order to derive the determinant formula, okay, what I need to do is first I need the property of the van der Waals determinant, which I will just state. I will not prove it just for lack of time, but if you're interested, I can say a bit more about that. So the proposition. So the van der Waals determinant squared, so delta n z, can be written as the sum over all possible permutation of n natural numbers of the determinant of z to the power k plus L minus 2 sigma k, which is the corresponding image under the permutation, over KL running from 1 to n. Okay. So the square of the van der Waals determinant can be written as the sum over all possible permutations of the group of Sn of these determinants. Okay, so this is a determinant of powers which are connected to the moments we want to look at, of course. And I mean, the proof is just straightforward. It's just about you take the van der Waals determinant, you apply the definition of the determinant, where you write the permutation in one. You write the product of delta n by itself, and you consider you choose the permutation index. In one factor, you choose one permutation index. In the other factor, you choose another permutation index, and just you work out the algebra, and you end up with this expression. Okay, there is no mystery about this, right? So it's just very straightforward, and just a few lines of calculations. So once you have this result, we can prove the lemma, the main one of the main result of interest in this particular context, where the delta n, the tau n, is equal to the determinant of the matrix of the moments matrix M n. Okay, so tau n can be written as the determinant of the moments. So yeah, let me see. I've got 20 minutes, and essentially the thing I want to definitely do is to prove the Adler-van Moerbeke theorem. Essentially prove that tau n is a solution to an integrable hierarchy, and in particular, I anticipate the result. Tau n is the tau function for the Toda hierarchy, and so given this, and the proof is based on this lemma that establishes the relation between tau n and the determinant of the moments of the matrix of moments. So the first thing I want to do, okay, so what I'll do, I'll move on to the next step until we can prove the Adler-van Moerbeke's theorem, and then I can return to the proof of this. If anyone is interested, I can return to this in any other moment. So let me use this time to clarify the connection with the integrable, with the integrability. Okay, so and so the moments matrix Mn contains information on the partition function. The next step is given Mn. Okay, we consider the semi-infinite extension of Mn. So I call it M infinity T, okay, which is a semi-infinite Hankel matrix. I expand this matrix in all directions. So it's Z1 to the power 0, okay, in all the to the right and to the bottom. Okay, it's a semi-infinite Hankel matrix. So once you have Mn, and you consider formally M infinity, so M infinity as a function of the t's, so M infinity is symmetric. What I can do is to write it as, what I want to do is to consider this decomposition s to the minus 1 times S transposed, okay, to the minus 1, okay, where S is a lower triangular matrix. Lower triangular semi-infinite matrix. Okay? So this is lower triangular, this is upper triangular. There is no loss of information in writing Mn in this way. Okay, I call this S to the minus 1 just for the following definition. So it turns out to be handy, but you don't have to do that. All right. So okay, given this decomposition, okay, we can state. So the Adler-van Moerbeke's theorem so I think there are several versions of this. I think the first appeared in 1995. So so given you have the moments, the semi-infinite matrix of moments, you consider this decomposition, and then we take the matrix S, and we define the matrix L equal to as S times lambda St to the power minus 1, okay, where, now apologize for the redundance notation, this time capital lambda is the shift matrix, okay, so it's a matrix with ones on the first upper diagonal, okay, so it's the shift matrix, and the S is induced by the composition of the moments, of the matrix of moments. So with this definition of L, okay, so we have that L is tri-diagonal and symmetric. Okay, so plus the derivative of L with respect to tk is equal to the commutator of 1 over 2 L to the power ks with L. Okay, I'm going to explain the notation in a moment. So L is defined in this way. So then it follows that L is a tri-diagonal symmetric matrix, semi-infinite matrix. Okay, I'm not going to say semi-infinite, it's understood from the definition, and the derivative of L with respect to Tk, okay, for all k larger or equal to 1, so for all the times, so L satisfies this equation. Okay, so those who are acquainted with integrability will recognize in this a Lax equation. So L is the Lax matrix, indeed, of the total lattice. So what is this quantity here? This is the kth power of L projected on the skew-symmetric, on its skew-symmetric part. So just to give an example, let me write so the skew-symmetric part. So for example, right, A, B, B, no, right, let me say A1, A2, B, B, B. So if I take the skew-symmetric, so this is a symmetric, so this is a symmetric matrix 2 by 2. The skew-symmetric part is a skew-symmetric matrix where the entries of diagonal entries are B and minus B. Okay, so just to give an idea of what this projection means. Okay, so L is tridiagonal and symmetric. So L to the power 2 will be fifth diagonal and symmetric, and the skew-symmetric part will be essentially a matrix where the main diagonal is 0, then you copy the upper triangular part into the lower triangular part and change the sign. Okay, so for a matrix of this kind is just this simple expression. So, and with this assumption, with these definitions, so L is the Lax matrix for the Toda system. Okay, so and the first equation corresponds to, if you write this in components, correspond. I will do this later. So the last session will be, in the last session we'll be looking at the details of this equation, what it means in terms of what is its interpretation as a dynamical system. Okay, so at the moment I want to just focus on this result that says that the matrix L so constructed is the Lax matrix of the Toda hierarchy. Okay, so by the way the system is constructed, by the non-trivial properties of the system, this hierarchy of equation is all compatible. Okay, but this is highly non-trivial. It's a chapter of the theory of integrable systems. All right, so let me use this the time left to prove this theorem. Okay, to see how this result is proved. Okay, so so the first thing to prove is that the matrix L is symmetric. Okay, but this follows essentially from the definition. All right, so what is L is S times m infinity s to the minus 1. So this is S m infinity is defined as s to the minus 1 s transposed to the minus 1 times s. Let me see. Did I copy it? No. Sorry, guys. I just went too quick. So L is defined as s times lambda s to the minus 1. So this is s lambda s to the minus 1. And then we can multiply by s transposed to the minus 1 times S transpose, okay, without changing anything. So in this gives us, this is M infinity. So this is L S lambda M infinity S transposed. Okay, this is the first bit. So now by looking at the properties of M infinity, so the derivative of M infinity with respect to Tk, okay, is equal to lambda k to the power M infinity times M infinity. Okay, lambda k is the shift operator. So remember what M looks like. So M looks like this. So z to the expectation value, z to the power 0, z to the power 1, z squared, and so on, right? And then you get z squared, and so on. So given the definition of rho, okay, the weight, when you differentiate with respect to Tk, you just drag a power in the from the exponential, a power z to the k. So every time you differentiate with respect to Tk, so you increase the moment you're calculating, and this is equivalent to shifting up this semi-infinite matrix by a suitable number of places. So if you differentiate with respect to T1, you shift, it's like shifting this matrix up by 1, and so on. Okay? So M is infinity is symmetric, so this means that lambda, so in particular, so it's nice to state this in general. So for k equal to 1, so since the left-hand side is symmetric, the right-hand side is also symmetric. So this means that lambda times M infinity transposed is equal to lambda M infinity. So, and therefore, so M infinity lambda transposed is equal to lambda M infinity. So lambda M infinity. Okay, I'm just using the symmetry, and then we want to use this. We want to use this property to swap this the order, to swap the order of lambda and M infinity. So this would be M infinity times lambda transposed. Okay. So once you have this, so it just what you get is L transposed. Okay. So then L is symmetric, but now L is symmetric. But what is this? So L is lower triangular times a lower triangular shifted up by 1. So this is a lower triangular times a lower triangular, okay, plus one upper diagonal. So this means that the result would be a matrix which is lower triangular plus one extra upper diagonal. But since it is symmetric, it must be tridiagonal. Okay, so L is symmetric and tridiagonal. So the final step is, if I may erase this part, so the final step is now to actual so yeah, the final step is to prove to find this equation given the definitions. So let's start from this equation for this property. So Mn satisfies a linear equation. Okay, so we start from, so the tau function is expressed in terms of an equation of a function of a matrix that is satisfies a linear equation. So, and this transformation and this definition of the Lax pair connects this solution to this linear equation to the solution of the nonlinear integrable system. Just to give a glimpse on what is the general picture, right? So what do we do here? The first step is to let's multiply by to the left and to the right by S and S transposed. So this is S. Let me write the right hand side first. Lambda k m infinity S transposed. This is S d m infinity by tk S transposed. And so the first thing is let's use the definition of m infinity here. So this is S to the minus 1, S transposed to the minus 1, S transposed, and then we copy the right hand side, S m infinity by tk S transposition, right? So this is equal to the identity, okay? So this is equal to the identity. And now what we can do here is to split this power of lambda to the power k. So we can write it as S lambda, and then we write S to the minus 1 S, then lambda, and so on, okay? Up to S lambda, S to the minus 1. Okay, so from here we go to here. So I split this lambda to the power k, and then I insert this identity written like this. And what does in the between? So this is L essentially k times. Okay, so this is just L k times. So what we get then so we get L to the power k. Okay, so the left-hand side is just L k times. And then I bring the right-hand side to the left, and then I get S, the derivative of m infinity with respect to tk, S transpose equal to 0. Okay. So now, again, now it's a matter of algebra, so we differentiate. We use the definition of m infinity, so S to the minus 1, S transpose to the minus 1, and then what we get from this from this expression. So we use this definition, and then we use also the fact that if we differentiate, so S to the minus 1, again the usual trick, the derivative of the identity is 0. So this allows us to reverse the order of S and S to the minus 1 when we expand this derivative here. And if you allow me to skip the intermediate result, I just write the equation that the equation we get as a result. So L to the power k plus the derivative of S with respect to tk, S to the minus 1 plus S transpose to the minus 1, the derivative of S transpose by tk equal to 0. Okay? So this equation, again, we have this equation, use the definition of Mn, expand this derivative, and use this property to swap the order between S and so this is So yeah, let me write the property. So minus s ds to the minus 1 tk equal ds by dtk s s to the minus 1. Okay, so when you plug this into here, then you end up with this equation for involving L and S. Okay, so now the next step is to split the equation in two parts. Okay, so essentially the logic for the splitting is related to what is called the AKS scheme, Adler constant seamless scheme, where who essentially discovered that the theory of the total lattice is related to the splitting of a Lie algebra. You can construct an integrable system, so a sequence of commuting flows starting from the splitting of a Lie algebra. So this is just to mention that what I'm doing here has a profound meaning in terms of algebra somehow. But what we need here is essentially to consider this projection. So we want to look at the lower triangular part So you see the lower triangle, I denote by a bracket with a minus the lower triangular part of the equation, and by the bracket with a 0, the diagonal part. The diagonal part. So, and in doing this, we extract from this equation two equations. So so what is so if we look at the project on the lower triangular part, this is LK lower triangular part, d by dtk s to the minus 1 plus s transpose to the minus 1 ds transposed by tk diagonal part. Right? So the lower triangular part includes the diagonal. So the lower triangular part includes the diagonal. So if you compare the top, so LK, the triangular part, so here I do nothing because S is already lower triangular. There is nothing we need to do here. And but S transpose, this last term is S transpose is upper triangular. If we isolate the lower triangular part, what's left is the diagonal part of the equation. And then if you take LK 0, if we take the diagonal part, we see that the first term is the diagonal part of LK, and then these two terms share the diagonal part. Okay, they are lower diagonal, upper diagonal. They share lower triangular, upper triangular. They share the diagonal part. So then we can just write 2 times ds by tk times s to the minus 1, 0, okay, equal to 0. Okay, so and then at this point, so we consider the lower triangular and the diagonal part. We introduce, so we're working with the space of matrices, and we consider the following according to this what has been done in this in the AKS scheme. So we split the algebra of matrices in two parts, in the direct sum of 2 parts. So S are the skew symmetric matrices, And the part that I indicate with B are the lower triangular matrices. Okay, so we split any matrix into a skew-symmetric part and then a lower triangular. Okay, let's look at an example just to visualize what we're doing. So suppose that we look at L, A, B, B, C. Okay, so L is a symmetric tridiagonal. This is quite trivial as an example, but what is L minus is A0, B, and C. L0 is A0, 0, C. And then LS is the skew-symmetric part, as I mentioned before, is as 0 on the diagonal, B and minus B. And then LB, okay, can be written as 2 times the lower triangular part minus L0, okay, which is A, 0, 2B, and A. Okay, so this would, so if L was a 2 by 2 matrix, this is what we would get, right? So we got, but this expression, L, the B projection of L, can be always written as 2L minus L0. Okay? And so yes, that's right. And so we got our 2 equations there, right? So let me just, okay, why am I saying this? Essentially, I want to express in this equation here we got the lower triangular projection. I want to replace this with this projection on with this projection. Okay, so the B, okay, the lower triangular matrices that constitute this this splitting of this algebra. Okay, so I didn't have the.
So the reason you're doing this.
Yeah. Yes. Yeah. And essentially, so this splitting is particularly important to construct the flows of the Toda hierarchy. Okay. So, but there is just a linear relation between the two, and then we can exploit that. So I will probably speed up a little bit, but hopefully without losing the logic. So if we express now, so we express now LK lower triangular part can be written as 1 over 2, okay, multiplied by LKB plus LK diagonal. Okay, so from this expression, so I can express the lower triangular projection in terms of B, and then I will substitute into the first equation. So if we substitute into the first equation, what we left with is this. So let me see if I can skip a step without losing. All right, let me do this. So 1 over 2. So substituting to the first, right? So 1 over 2 LKB plus 1 over 2 LK0 plus derivative of s with respect to tk, s minus 1, plus s transpose to the minus 1, ds transpose tk, and this is the diagonal part, right? And the diagonal part. But now you see, in this substitution, we have LK0, which I can take from the second equation, right? So LK0 is minus 2 times ds by tk, s minus 1, s minus 1 lower triangular part, in this so a diagonal part, and these two cancel out, right? So then what we get is what we left up to a multiplication on the right by s is the derivative of s with respect to tk, all right, plus 1 over 2 L to the power k b times s equal to 0. Okay, so I can probably remove this bit to clean a little bit s equal to 0. Okay, so this is this is the first equation. Okay, so so now we are very close to the result now. Now, what we need to prove is the following thing. So, what I can prove, okay, is that L. I mean, it's not a surprise if you bear in mind the Lux theory. So, the Lux operator. When you have a Lux operator and you want to describe the integrable system, you expect to have some eigenvalue problem, right? And what I want to do now is to derive an eigenvalue problem that, associated to this, the compatibility will give us the final equation, the Lux equation for the Toda system. So now introduce. So the vector, let me call it chi z, the transposition, which is essentially a vector of monomials of the type 1, z squared, and so on. Okay, and then let's given the matrix S, the lower triangular matrix S, coming from the factorization of M, let's define these polynomials. I call them P equal to S applied to chi. Okay, so we're talking about formal infinite vectors and still formal infinite semi-infinite matrices. Okay? So now let's calculate L applied to P. So what is this? This is L, P is S chi, okay, and then apply the definition. L is S lambda, S to the minus 1, S chi, right? So, and this is S lambda chi. But what is lambda? Lambda is the shift operator. So, if I apply lambda to chi, it's like multiplying chi by z. So this is S times z chi, and then this is z times S applied to chi is P. So the matrix, semi-infinite matrix L satisfies this eigenvalue problem. Okay, so P are polynomials, and these polynomials P actually turns out, now we can't go into this detail today, but P are orthogonal polynomials, and these orthogonal polynomials with respect to, guess what, the weight rho, so are orthogonal polynomials with respect to the weight rho, and these are the eigenfunctions of this Lax matrix L. So what we will prove is the Lax matrix of the total system. So now we have these two equations. So this equation for S involving S and L, and this equation for this eigenvalue equation for L. Now we got these two equations, and we can check the consistency of these two equations. Okay, so let me copy. We got this system, and then LP equal to ZP. Okay, we got these two equations. So I copy that, and then so, and I think I need to stop. I need to stop in a moment. So, right, okay, the idea now is straightforward. What I do, I take the second equation, I differentiate with respect to k, so I get dl by tk times p plus l dp by tk equal to z dp by tk. But then we have, so p is defined as s chi, so S of t chi of z. So when you differentiate p with respect to tk, it only affects the part, the t dependent part encoded in S. So when I have the derivative of p with respect to k, we produce a derivative of S with respect to tk. And then we can use the equation above to express the result in terms of LK projection B. Okay, so now, okay, I'll just save you the intermediate detail. But what we get is once we use this expression here and substitute the first equation, we get that dl by tk is equal to 1 over 2, so LKB minus LKBL, and then we use the fact that L is equal to, the projection of LK due to this, the algebra splitting, so LK, okay, is equal to LKS plus LKB. So we can replace B, the projection B in terms of the projection S, and with L. So this is 1 over 2, the commutator of LKB. LKB, L to the power k b, and then if we use this equation, since L commutes with itself to the power k, we end up with 1 over 2 L to the power k s L, which is what we wanted to prove. Okay, so we just express projection B in terms of projection S, so it changes the sign. Then we have the additional term L to the power K, which commutes with L. So what is left is just L to the power K L S with L. Okay, so and this is the result, and showing that the Lax matrix, which we can think of as A3, and so on, B1, B2, B3, and so on, for diagonal B1, B2, B3, and so on. So the Lux matrix, if you write the Lux matrix explicitly, okay, so, and you substitute into this equation, so DL. So, for example, for k equal to 1, you get a chain of equations involving A's and B's, and that would be the total lattice equation in those that are called Flaschka variables. Okay, these variables are not the original dynamical variables. It's a different set of variables. Let me write the equation, the first equation. So dAn by T1 is equal to Bn squared minus Bn minus 1 squared, and then dBn by T1 is equal to Bn over 2 An plus 1 minus An. So this is the first equation of the total hierarchy in the so-called Flaschka variables. So A corresponds to the moments, so are related to the moments of. So okay, for those not familiar, the total lattice is a one-dimensional chain of particles with nearest neighbor interaction of exponential type, and the variable A is the momentum of each particle, as the variable A's are the momentum, and the B are essentially related to the exponential of the displacement from the rest position. So the diagonal contains the momentum, the off-diagonal part the displacement from the rest position. All right, okay, so this is all for today. Thank you guys for